Good morning, and welcome to our second piece here on regression and, of course, correlation. We left off last class looking at a relationship between GPA and starting salary. And I asked you guys, what type of, what do you think this correlation is going to be, positive or negative? You said positive. Yeah, as GPA increases, starting salary increases. It kind of looks like what the data is telling us here. Now let's determine how strong this correlation is. We have to square each x and y data point and create the product. We're getting the data set ready to compute Pearson R. 2.9 squared, 8.41. 3.81 squared, 14.52. 10.24. 5.86. 15.52, 4.2, 5.06. We square each y data point, and by the way, these figures are times 1,000, right? So this is 38,000, 48,000, and so on and so forth. 38 squared, 1444. 48 squared, 2304. 1444. 35 squared, 1225. 50 squared, 2500. 31 squared, 961. 37 squared, 1369. We create the product. This times this, 2.9 times 38, 110.2. 3.81 times 48. 182.9, 121.6, 84.7, 197, 63.6, 83.3. And again, we make sure we do this correctly. I know that's obvious, but it's just real easy to make a little mistake on your calculator because you're rushing or something. So we got to get these numbers right. We have 7 bivariate data points. N is 7. We have 7 pairs of scores. Sum x is 20.57. Sum x, the quantity squared, 20.57 squared, 423.12. Sum x squared, 63.81. We're going to take a mean of x, and we know we're going to use that to compute a down the road. The mean of x, sum x divided by n, 20.57 divided by 7, gives us an x bar 2.94. So on average, in terms of our mean, our sample has about a 2.94 cumulative GPA. Sum y, 277. And we take that number and we create the sum y quantity squared, 277 squared, 76729. Sum y squared, 11247. And we're going to take a mean of y. We'll use that, of course, to compute a. Y bar, sum y divided by n. 277 divided by 7 is 39.57. Or $39,570 mean starting salary for our sample. Sum xy, 843.3. And it looks like we're ready to go. Am I doing this right, class?
Yeah.
Good. I'm glad I got it all right. Next step, compute Pearson R. We just plug in. Pearson R is sum xy, 843.3 minus the sum x. I did it again. Look at that. Sum x, 20.57 times the sum y, 277 over the n of 7 all over square root of this first piece, sum x squared, 63.81, minus the sum x quantity squared, 423.12, over the n of 7, close the bracket, open up the next one, sum y squared, 11247, minus the sum y quantity squared, 76729, over the n of 7, close the bracket. Now it becomes simple order of operations. Again, you know, this whole quantity subtracted from this whole quantity subtracted from this whole quantity subtracted from this. And so we do that. Pearson R, this whole quantity subtracted from this is 29.32 over the square root of this divided by this, and then all subtracted from this is 3.36. This divided by this, all subtracted from this, is 285.71. Close the bracket. And we continue. Pearson R, we have this positive numerator, 29.32, over the square root of this product, this times this, 959.99. R is 29.32. The square root of 959.99 is 30.98. In this case, Pearson R is positive 0.946. R squared, 0.895. 1 minus R squared, 0.105. Sometimes you'll see Pearson R reported in 3 digits. Don't ask me why. It just is. Interpretationally, we can say that we've detected a pretty strong positive relationship between GPA and starting salary. Pretty strong relationship. Not a whole lot of prediction error, no. We could plot this, these 7 bivariate data points, but just for the purposes of illustration here, in a scatter plot, for a correlation of this positive magnitude, 0.946, we would have a pretty tightly constricted set of bivariate data points, going up and to the right, down and to the left, with this elliptical configuration, with our regression line going right up the center. We have about 89.5% shared variation for our coefficient of determination. Interpretationally, we would say 89.5% of the variation in y can be explained or predicted by the variation in x. We have about 10.5% unshared variation. This is the coefficient of non-determination. And we'd say about 10.5% of the variation in y cannot be explained or predicted by the variation in x. So this is the correlation piece kind of like, phase one, so to speak. We said if, as correlations increase in strength, it gives us the ability to predict y from x using this method called simple linear regression, where we build this simple linear regression equation. And we said the other day, once we do this, we can then extract any x data point out of the data set, plug it into the equation, and predict a y. But we're always predicting with error. And so we'll compute that measure of prediction error in a minute. Before we do that, let's start with b, the slope. And the good news is all our information is right here. B is, again, the numerator of Pearson R. Divided by this piece of the denominator. So we already have the numbers in front of us. The numerator for B, the numerator for Pearson R, we actually computed to be 29.32. And then this denominator for B is right here. We computed it to be 3.36. Our slope in this case is 8.73. Okay. Pretty substantial rise over run, if you ask me. We'll then compute A, the y-intercept. We know that to be the mean of y minus the b we just computed times the mean of x. And we have all our information here. Y-intercept is the mean of y, 39.57, minus the b we just computed, times the mean of x, 2.94. And if we run this equation through, we end up with an A of 13.9. Great. We have B and A. We can now put our equation together. Our predicted y, y prime, is our slope, positive 0.873x plus 13.9. Now again, we said that once we achieve this, we can extract any x data point out of the data set. We'll be doing that in a minute. And predict a y. But again, we're not predicting perfectly. We're predicting with some error. We call this prediction error. The prediction error, again, is just this scatter. It's the scatter of bivariate data points around y prime. So we need to compute this measure of prediction error. And we know this measure is a form of S that is appropriate to the bivariate world. It's called the standard error of the estimate. And it's a form of S. We call it S subscript ESTY. Small est, larger y. And it has a formula attached to it. It's the standard deviation of y times the square root of n times the coefficient of non-determination over n minus 2. So we see this pesky little s sub y, which is the standard deviation of this y column of scores. This requires us to compute that. We won't do that. It's going to take a little too much time for us. What I will do is actually provide that for you, and I will always provide that for you. In this case, The standard deviation of the y column of scores is 6.39. So if we were to have done this, if we were to have computed S with this column, we would have gotten 6.39. We can now compute our standard error of the estimate. It's S sub y, 6.39, times the square root of our n, which in this case is 7, times the coefficient of non-determination, 0.105, over n minus 2. 7 minus 2 is 5. We just bring this thing down. The standard error of the estimate is 6.39. This times this divided by this is 0.1456, or something pretty close. This is something pretty close. The standard error of the estimate is 6.39. The square root of 0.1456 is 0.3816. The standard error of the estimate in this case is 2.44. So in this case, class, what is one z unit equal to? What is one z unit equal to? 2.44. Yeah, one z unit equals 2.44 y units. So one z unit converted is $2,440 starting salary. Now, we wonder, I wonder what the best prediction would be for a student who graduates with just a vanilla 3.0 GPA. I wonder what the best prediction would be for a student who scores, who graduates with a GPA of a B average, 3.0. Let's do this. We'll say, so, ... for an x equal to 3.0 GPA, ... y prime equals, and if you're wondering where I got the 3.0, I just sort of picked it arbitrarily. I will give you that x. Just plug the x in. Y prime equals b, 8.73, times 3, plus the y-intercept, 13.9. Bless you. And if we run this through, y prime is 40.09. Or $40,090 starting salary. $40,090 starting salary. What does this mean? It means that based on the data at hand, our best prediction for a kid graduating with a 3.0 average is that he or she will earn $40,090 starting salary. So, science is all about explanation and prediction. Science is all about explanation and prediction. So if you're wondering all about that, here it is. Again, observation, measurement, and data analysis. Yeah. We said that this scatter plot is actually a little system. It's a little system of standard normal distributions. It's a little system of standard normal distributions with this y prime serving as something really similar to a mean. And if we digest that, and conceptualize that, so to speak, and if we just revisit this standard normal distribution, we are very familiar with the characteristics of the standard normal distribution. We know that the mean, median, and mode are all identical. We know that we would typically put mu here or x bar here. We'll put y prime here. We know y prime is 40.09, and we can partition this thing just like we always did. And draw our areas under the curve. And we're going to treat this standard error of the estimate just like we would any other form of S. We're going to go out addition-wise this way, back subtraction-wise this way. 40.09 plus 2.44 is 42.53. 42.53 plus 2.44 is 44.97. 44.97 plus 2.44, 47.41. 40.09 minus 2.44 is 37.65. 37.65 minus 2.44, 35.21. 35.21 minus 2.44, 32.77. We have raw score scale. We can draw our scale of Z. And we can combine, like we did and like they do in our textbooks, we can combine some of these areas. This plus this, 68.26%. Add this, 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 and this, about 95%. And just about the total area constitutes a little over 99%. And once we do this, again, based on the data at hand, we can make some statements relative to the likelihood that, and again, based on our information, based on this relationship, the likelihood that a kid graduating with a 3.0 GPA will earn a starting salary within a certain interval. This is the best prediction, but it's not the only prediction. There's about a 2 in 3 chance that, about 68.26% of the kids are going to earn between $37,650 and $42,530. A very small percentage are going to start out above $44,970. Now again, there are more variables associated with starting salary besides GPA. That's pretty obvious. And we also know that the kids that are majoring in engineering or whatever, computer science, are going to probably start out up here. Kids majoring in education, sociology, psychology, human services will probably start out down here. What this is telling us is that we're almost absolutely certain that a kid graduating with a 3.0 GPA, again, based on this information, will start out earning between $32,770 and $47,410. Simple linear regression, predicting y from x with some error. So again, what did we do here? Measure of relationship. measure of shared and unshared variation. Then we proceeded to phase 2, the ability to predict y from x with some error, correlation and regression. Now, you see a lot of information on the board here, but not a whole lot of sophisticated math. This is just pretty much simple arithmetic. Okay? The importance of this is to, get what's going on. Just keep it real simple. Relationship between x and y, shared variation, unshared variation, and the ability to predict with a bit of prediction error, in this case. Correlation and regression. Okay, take a minute, take a deep breath, a couple deep breaths, maybe talk to your neighbor while I erase this board. And we're going to talk about some conceptual things. I was sitting in a statistics class one time when I was a student, and the professor told us the correlation between SAT scores and college GPA. SAT is specifically designed to predict success in college. That's why it's there, supposedly. But if you look at the data, the correlation between SAT scores and college GPA is 0.40. It's kind of a moderate positive relationship, and it's statistically significant. If we were to draw a scatter plot for a correlation of this magnitude, the scatter plot would look something like this. We would have a pattern. We don't have total random, but we would definitely have a pattern. We would have that elliptical configuration, so to speak. But the data points would be, rather spread out. And of course we would have our regression line, going right up the center. But this illustrates a really good point. We always have to remember, relative to correlations and prediction error. Remember, as correlations increase, prediction error decreases. As correlation strength decreases, prediction error increases. Let's take a look at this. Here's an individual who actually scored pretty high on the SAT, but has a low GPA. This is the line of best prediction, but it's not the only prediction. We have error. Here's a kid, high GPA, high SAT, low GPA. I wonder why that is. Why do you think that is? Yeah, he's not studying. He probably went up to the University of Florida, and all maybe first time away from home, all this freedom. And he's a pretty bright kid, and yeah, he scored well on the SAT, but he's just not doing any work, and he's flunking all his classes. But it happens all the time, by the way. A lot of distractions when you go away to school. Here's another individual who shows up, takes the SAT, doesn't do real well. I remember years ago when I took the SAT, up in Michigan, it was at some other high school besides mine. It was at 8 o'clock in the morning on a Saturday after I had I was an athlete, so we had a football game the night before, and I'm tired. So I show up for this test at this strange high school. I don't think I ate any breakfast, of course. I'm sitting there, I'm scared. I got some real cranky moderator, giving me the test, and I'm kind of sitting there shaking, going, This particular kid scores low on the SAT, has a high GPA. Wonder why? Well, he's working. He's studying, He's motivated. He's, doing things on a daily basis to, be a good student. Has a good attitude, comes to class, really works hard. This is, prediction. The hurricane, this is the best prediction for a hurricane, but it's not the only, it might go this way, and it might go this way, Prediction error, yeah. And again, what we're talking about here is just this case of simple linear regression. We, in intro stat courses, this is introductory. We introduce regression using this. But the reality is, you never see this in the real world. But we have to start somewhere, so we start you out with this. But in the real world of scientific research, what you do see a ton of is this thing called multiple regression. And a typical multiple regression equation might look like this. In multiple regression, compare these two equations. This is just an extension of this. This just has more predictor variables. In multiple regression, we have multiple predictors predicting one outcome. And you see a lot of this in the scientific journals. Because there's a lot of variables that can predict an outcome. For instance, college GPA. One predictor, might be, one predictor might be SAT, of course, But another predictor, as you guys mentioned, might be just, motivation, study time. Typically, students who really do a lot of studying, spend a lot of time with the material, do well. It's just because then you have an exam, you spend so much time with this material that you look at the exam questions and it's just, just, you know what I mean? It's another predictive variable might be high school GPA. They told me that the best predictor of future behavior is what? Past behavior. Well, that's not always the case. We can certainly change our behavior, but typically we're going to behave tomorrow just like we did today and yesterday. If we could go on and on about that, but multiple regression, multiple predictor variables predicting one outcome. Correlation does not infer causation. Correlation does not infer causation. This is a basic concept that you cannot forget. Just because two variables are highly related with each other does not mean, or does not necessarily mean, one caused the other. Just because two variables are highly related doesn't necessarily mean one caused the other. The truth of the matter is, there's a ton of correlations out there in the natural world, some of which are pretty meaningful, others are not. There could be, we could take a sample of 1,000 individuals and look at the relationship between blades of grass on their lawn, the number of blades of grass on their lawn, and the number of hairs on their head. And we just might find a significant correlation. Does it mean anything? No. No. Correlation is simply a measure of relationship. Simply a measure of relationship. Now, correlation could be used as a precursor to an experiment. We know experiments are designed to provide evidence for cause and effect. So correlation can be a precursor to an experiment, but in and of itself, correlation does not infer causation. So on any exam question, class, on any exam question, if you see anything, any answer response that implies that one caused the other, it's not correct. It's not correct. Correlation is simply a measure of relationship. Okay, this Pearson R thing, this Pearson R, we see a lot of, and we also see a lot of ratio scales and some interval scales. Remember we said the ratio scale is probably the most widely used scale in science. Continuous data. So Pearson R is typically used at the ratio and interval levels in terms of measurement. We have another measure that's designed to measure for relationships with ordinal data. It's called Spearman's rho. Spearman's rho. It's a measure of relationship between x and y designed for data at the ordinal level. We know ordinal data is that rank data, rankings, standings, whatever. We have another measure for data at the nominal level. And there's actually a couple of those measures. One is called the point Biserial correlation coefficient. The point Biserial correlation coefficient. There's another one called the phi coefficient. Again, measures of relationship designed to, look at the association between x and y with data at the nominal level. Okay. Correlation has a sister measure. It has a measure that's very, very closely related to it. It's called covariance. Covariance. Correlation is considered a standardized measure. And it's considered standardized because essentially a raw bivariate data set is reduced to another scale, isn't it? That scale ranges from -1 to +1, and we call that scale Pearson R. So every time we compute Pearson R, we're simply reducing a bivariate raw data set to another scale that ranges from -1 to +1, and we interpret those correlations accordingly. Covariance is also a measure of relationship, just like correlation, but it's considered non-standardized. Because if you were to compute covariance, per se, on a set of bivariate data, you would get these like really, really large positive numbers or really, really large negative numbers, like R equals 273.68. And so that covariance estimate ends up getting reduced back to the Pearson R for interpretation. So, Just, this term, if you remember when I first introduced the concept of correlation, I said the extent to which two variables change together in a systematic way or covary. I use the term covary, and that's where this comes from. They, covary, vary together. Positive relationships, negative relationships. Okay. The results of research are always tentative. The results of research are always tentative. Tentative. What does tentative mean? Tentative. Maybe inconclusive. The ball game is in the 7th inning and the score is 5-3. The results are tentative. Why? Because the game's not over yet. Okay, so the results of research are always tentative for many, many reasons. Many reasons. Number one, we always got to get more data. The results are in, but there's always more to get. The scientific process is ongoing. The results of research are tentative because we could have a bias sample, we could have confounding variables that might be making our results less than accurate. So in a general sense, the results of research are always tentative. And in the correlational sense, the results of correlational research are always tentative as well, for a few reasons. Now again, this is an intro stat course. Google introductory statistics, or even just the Wikipedia, you're going to see a lot of these terms, one of which is the notion of the spurious correlation. The results of correlational research are always tentative because we may have a spurious correlation. A spurious correlation is a correlation that is artificially high or low as the result of some confounding factor, as the result of some confound. We know what a confound is, don't we? We've been in this class now for a month. We better know what a confound is. If you don't know what a confound is, off the top of your head, you're not with it. You're not studying. Okay? It's like being in baseball now for a month and you still can't hit a curveball. Why? Because you haven't been practicing. Okay? We know the confounding variable is that some other variable associated with the IV or the DV that could be affecting our results accuracy. For instance, back up a little bit, that correlation of 0.946 that we found between GPA and starting salary. Well, that's great, but you know what? There might be some other variable associated, some other unseen variable associated with GPA or starting salary that may be making that R a little bit bigger than it should be. So we always have to interpret the results of research with a little bit of caution, a little bit of healthy skepticism. That's a good word. Healthy skepticism. You don't believe everything you read in the newspaper, especially these days. When Yahoo News comes up on your, and you're looking at all this, the sensationalistic stuff, you really have to wonder about its accuracy. Okay. The results of correlational research are always tentative because we may have what we call curvilinearity. We may have curvilinearity. If we look at a scatter plot, and that scatter plot looks like this, We have a nonlinear relationship. We have a curvilinear relationship. Pearson R is meaningless. So we might see a Pearson R reported. We have no idea what the scatter plot looks like. The people reporting this Pearson R really had no idea what they were reporting. And if the scatter plot looks like this, Pearson R is actually meaningless. The results of correlational research are always considered tentative because statistical outliers, those extreme scores, may affect the magnitude, may artificially inflate or deflate R. Statistical outliers, those extreme scores, may artificially inflate or deflate R. Reliability and validity. We remember those. We talked about them when we spoke of measurement. Reliability is consistency of measurement. Validity is considered accuracy of measurement. Pearson R is used extensively. It's used a ton in studies designed to establish evidence for reliability and validity. So R is used in both of these. Let's see how this works. Let's suppose we're trying to establish the reliability of our weigh scale. Let's try to establish the reliability of our weigh scale. This is typically how it's done. We have X and Y. Let's call X time 1, Y time 2. And let's say we have 6 subjects. Subject number 1 gets on the scale at time 1. He weighs 168 pounds. Gets off the scale, waits about 30 seconds, drinks a glass of water, gets back on, he weighs 169. Subject number 2, she gets on the scale, she weighs 118 pounds, gets off the scale for about 30 seconds. During that time, she drinks a glass of juice, gets back on, weighs 119. Subject number 3, he gets on, he weighs 205, gets off 30 seconds, gets back on, he weighs 205. Subject number 4, he gets on the scale, he weighs 176 pounds, gets off the scale for about 30 seconds, drinks a glass of water, gets back on, he's 177. Subject number 5, she gets on the scale, she weighs 107 pounds, gets off the scale for about 30 seconds, gets back on, she's 107. And subject number 6, he gets on the scale, he weighs 186, gets off for about 30 seconds, gets back on, he weighs 186. So we have a set of X and Y data, and if we look at these numbers, we see a lot of similarity. If we were to compute Pearson R on this set of numbers, it would be, just take my word for it, it would be very high and positive, like 0.96 or something. And it is this number which actually tells us that this scale is reliable. So it's this number that tells us, that the scale is reliable. So the higher Pearson R estimates are, the more reliable our scale is, the more consistent we're, and we see that our instrument is measuring very consistently here. Validity answers the question, is the instrument measuring what it's supposed to measure? Is the instrument measuring what it's supposed to measure? Oop, jeez. Okay. That was a Chevy Chase move right there. Yep. On film, of course. Let's suppose we always wanted to be a pilot. Let's say we always wanted to fly airplanes. So we go up to Vero or down to Stewart at the airstrips there, and we take flying lessons. Okay, we go through the whole course of study, and we're right at the end of our flying lessons, and we're ready to take a written exam. So we're going to call variable x the actual written final exam. The written final flight exam. The paper and pencil written final flight exam. And we're going to call y the actual ability to fly the plane. The ability to fly the plane. Now, wouldn't you want, I mean, knowing what we know about correlation and regression, about the ability to predict y from x, wouldn't you want, you know, this written final exam to be highly predictive, right, of the ability to fly the plane? Yeah. Wouldn't you want this exam to be able to predict with really low prediction error? Absolutely. So you know what? This flight school has amassed all this data, you know, over all these years, you know, correlating the written final exam scores with the solo score, you know, the ability to fly the plane. And so let's say, you know, they computed a Pearson R of like positive 0.94. Well, you know what? That's a pretty doggone high positive correlation. And people can look at this number and they can say, you know, pretty highly predictive. This is pretty highly predictive of the ability to fly the plane with really low prediction error. This is a pretty accurate, this exam has extremely high predictive validity. Predictive validity. There's a number of different types of validity. This is called predictive validity. So the takeaway from this is just simply, you know, correlation is used extensively in studies to establish evidence for reliability and validity. And finally, correlations are typically displayed in the literature using what we call the correlation matrix. The correlation matrix. And the correlation matrix can actually be, you know, can be pretty large. And, you know, studies can contain a lot of variables. You know, a lot of variables. And so the matrix is a real efficient way of reporting the results of correlation. Let's say we have 5 variables. You know, they would tell you what they are. You know, they would list them. And then they would create a matrix where we have, you know, variables along the top and down the side. And they would create this matrix with one going down the diagonal. And I'm just going to you know, pick some numbers out of thin air here. The correlation between 1 and 1 is 1 because it's the same variable. 1 and 2, I don't know, whatever, 0.38. 1 and 3, you know, 0.86. 1 and 4, negative 0.17. 1 and 5, negative 0.03. The correlation between 2 and 2 is 1 because it's the same data, right? 2 and 3, positive 0.16. 2 and 4, positive 0.29. 2 and 5, negative 0.13. Correlation between 3 and 3 is 1 because it's the same data. 3 and 4, you know, negative 0.48. 3 and 5, negative 0.14. Correlation between 4 and 4 is 1. 4 and 5, you know, positive 0.31. And the correlation between 5 and 5 is 1 because it's the same data. Now you see correlations on this side and nothing on this side because this would actually be the mirror image of this. For instance, the correlation between 1 and 2 is 0.38, so the correlation between 1 and 2 would also be 0.38. So typically they'll just not include this to make it easier to see. But scientists and researchers look at this, and there's a lot of information contained in this, and they might say, oh man, look at the correlation between 1 and 3 here is 0.86, pretty high and positive. I wonder if one causes the other. They can, all kinds of things that you can do with this correlation matrix. Okay, that ends the section 1 of our material. We're going to have an exam Tuesday morning, and I'd like to talk about that. Do a little bit of reviewing. This exam will consist of 73 questions. 73 questions. Some of them will be, if you've been studying, some of them will just be no-brainers. Some of them will require a little bit of thought, of course. About 15% of this exam will be computational. About 15% of these exam questions will be computational. In other words, you'll do some computing. You might do some work with means, medians, and modes. You're going to compute a variance and standard deviation, of course. You'll maybe do some work with Pearson R, and maybe a little work with regression, whatever. But most of the questions, about 85% of your exam questions will be conceptual in nature. Why? Well, because as you see, and I said the first day of class, statistics is a language. It's called the language of science. And now you see why. There's just a lot of terminology involved, here. There's a lot of things, a lot of conceptual stuff that we have to learn. So, we started out on the first day of class emphasizing that statistics is a very, very important part of the scientific method. We talked about the difference between descriptive statistics and inferential statistics. Descriptive stats are a situation where we organize, summarize, and present data. We basically do it 5 different ways, don't we? Frequencies, central tendency, dispersion, position, and then finally relationships. We said inferential statistics is a situation where we take the sample information that we get in terms of description, and we attempt to generalize those results back to the population from which the sample was selected. We introduced some really basic statistical terms in that first day. We said scientists are in the business of studying populations, whole sets of individuals or entities or whatever that they're interested in studying. We said that most of the time, whole populations, like all the mosquitoes in St. Lucie County or all the IRSC students, are hard to study because of time and money. So instead we take samples from populations and study them. We said ideally scientists take random samples whereby each member of the population has an equal likelihood of being selected. And we said that if a truly random sample is achieved, we can then generalize those sample results back to the population from which the sample was selected. Why? Because every member of that population had an equal likelihood of being selected, so that sample is as representative of the population, theoretically anyway, as it can be. We talked about dependent variables and independent variables. The dependent variable is the variable we measure. It's just the data. So any data that we analyze is a dependent variable. The independent variable, and this segued into a discussion of the experiment, you know, the true experiment, whatever. The independent variable is the variable we manipulate. It's the type of treatment administered. So the independent variable is the manipulated variable. The variable we manipulate to measure for its effect on the dependent variable. So in the experiment, the IV, the independent variable, is the cause. The dependent variable, the dV, is the effect. We went over that headache pain study. And we identified population, sample, IV, dV, and the ability to generalize. You'll have a set of questions on the exam that will require for you to do that. We said that that headache pain example is an example of a true experiment because it satisfies 3 criteria. Use of a control group, manipulation of an independent variable, and the element of randomization. We said that most experiments out there, though, are quasi-experimental because of the lack of random sampling. Biased samples. And we described the characteristics of biased samples, you know, whereby every member of the population doesn't have an equal likelihood of being selected. So in terms of the experiment, pretty high likelihood that the groups are not equal. We said that randomization actually spreads the risk of the effects of those any confounding variables equally across the groups. We know a confound is some other variable that could be affecting the IV or the dV, making our results less than accurate. Okay. So in non-random samples, in those biased samples, no generalization beyond the sample. They're called sample-specific results. Know your symbols. In fact, at this point in the semester, I'm assuming that you just know, you automatically know your symbols. I gave a little spiel on empirical research, what that actually is. Helps us answer, it's scientific research. Helps us answer questions. I talked about operationalization, research design, and so on. I covered summation, which we did a lot of course, in our computations. And then I went into measurement. The act of assigning numbers to observations in terms of how, using a set of rules. And we call those rules scales of measurement. You'll have questions on scales of measurement. Ratio, interval, ordinal, nominal. Know the characteristics of those. So I'll give you a situation. You tell me what type of scale it is. Reliability and validity. Reliability is consistency of measurement. Validity is accuracy of measurement. We then went into descriptive statistics. I talked about frequency distributions. That's kind of a no-brainer. They're counts. No questions on frequency distributions. Measures of central tendency, that index of central location that we use to describe frequency distributions. Mode, median, and mean. Mode's the most frequently occurring score. Median's the middle score. Mean is the arithmetic average. The median is the 50th percentile, also called Q2, right? If we have an odd number of scores, the median's right in the center. If we have an even number of scores, take the two middle scores, add them together, and divide by 2. I talked about the characteristics of the normal distribution. Mean, median, and mode are all identical, or pretty close to identical. And I also talked about the characteristics of non-normal distributions, and I remarked and I emphasized that one of the characteristics of the mean is that it is affected by extreme scores. So extreme scores can pull the mean over into its direction. So in non-normal distributions, the mean is not, it can be misleading. It's not an accurate measure of central tendency. the median is. So I may give you a data set, and you inspect it. If you see extreme scores, know that the mean isn't an accurate measure of central tendency. The median is. I talked about skew, positive and negative skew. Know the characteristics of skew. If we remember, the mean, median, and mode are not identical or close to identical. Know those configurations. I talked about measures of dispersion, descriptive statistic number 3, the degree to which data points are spread out from each other. I talked about homogeneity and heterogeneity. I went into great detail using the definitional approach. You're going to have some questions on that definitional approach. Okay, it's all in your notebooks there, guys. But we'll be computing using the computational approach. Variance and standard deviation, the degree to which our data points are dispersed around the mean. In the definitional approach, I'll ask you some questions about the sum of squares, the sum of the deviation scores. Know that model, that descriptive model. We'll be computing using the computational formula. We then went into measures of position, descriptive stat number 4. Determination of percentile rank using this process called standardization, whereby we transform raw scores to another scale to create standard scores, which we call Z. The transformation of raw scores to Z scores for the purpose of determining percentile rank. You'll have some questions on that, where I'll give you the mean, the score, and the standard deviation. You compute Z, and then tell me what the percentile rank is. Then we went into correlation. Descriptive stat number 5, I told you that this is probably the most involved of the descriptive statistics. Now you see why, but it's also very, very widely used. The relationship between X and Y, it is linear. Know the characteristics of negative and positive correlations and their scatter plots. Know what the scatter plots look like, correlation strength, and so on. We said if correlations are strong enough, it gives us the ability to predict Y from X using this procedure called simple linear regression, where we build this regression equation, X being the independent variable or predictor, Y prime being the dependent variable or predicted variable. We said we're never really predicting perfectly because we're predicting with error. And that error is nothing more than that dispersion, that scatter. As correlations increase in strength, prediction error decreases. We talked about multiple regression, that case where we have multiple predictors predicting one outcome. We computed Pearson R, the measure of relationship, R squared, the coefficient of determination, that measure of shared variation, 1 minus R squared, the coefficient of non-determination, the measure of unshared variation. We said Pearson R is mainly used at the ratio and interval levels. Point biserial correlation and phi coefficient are used at the nominal level. Spearman's rho is used with data at the ordinal level. Correlation has a sister measurement called covariance. Covariance is considered non-standardized, whereby correlation is considered standardized. I gave some words of caution. The results of research, correlational research, are always tentative. We may have a spurious correlation. We may have curvilinearity. We may have outliers that affect the magnitude of the correlation. Correlation is used extensively in studies designed to provide evidence for reliability and validity. And correlations are typically displayed using the correlation matrix. Now, I'm going to do something for this first test that I don't normally do on any other tests. And that is, I'm going to email you a copy of my lecture notes. Okay, I'm going to provide this for you. And I only do this for this exam 1. So I will see you folks at 9:30 on Tuesday morning. The exam will last, until about a little bit before 10:45. There's usually no problem in getting the exam finished. Thank you for being here, and I will see you Tuesday morning.